This is ELC131, Circuit Analysis 1, and this presentation covers low pass and high pass filters constructed with RC and RL combinations. Now, we look in Figure 1 and we see that there is a plot of capacitive reactance and inductive reactance as a function of frequency. And one of the competencies that I hope you come away with is the ability to look at an RC filter circuit and determine whether it will function as a low pass filter or a high pass filter. And what I've always done is look at the reactance of the capacitor at extremely low frequencies and extremely high frequencies. So when we look at X sub C at low frequencies, see that X sub C is extremely high. So at low frequencies, I can replace the capacitor with an open circuit. And at high frequencies, X sub C is extremely small. It approaches zero. So at high frequencies, I can replace this capacitor with a short. So looking at the circuit of Figure 2, at low frequencies, I can replace this capacitor with an open, and the only path for current is through the filter resistor and the load resistor. And at low frequencies, the output voltage, the voltage across the load resistor, will be at its maximum. However, at high frequencies, I replace the capacitor with a short, and again, that places the output or makes the output shorted to ground, and the output voltage, the voltage across the load resistor, will approach zero or be at its minimum because no current will flow through the load resistor. Now, looking at the circuit of Figure 3, an RC high pass filter, again at low frequencies, I replace the capacitor with an open, and there is no path for current through the load resistor, so the output voltage will be at its minimum. However, at high frequencies, I replace the capacitor with a short, and this will make the output voltage equal to the source voltage. The output will be at its maximum. Now let's look at RL filters. Again, in Figure 4, we see a plot of capacitive reactance and inductive reactance as a function of frequency. And again, I hope that you'll come away from this presentation with the ability to look at RL filter circuits and determine whether they will function as low pass circuits, low pass filters, or high pass filters. So we look at the inductive reactance as a function of frequency, and again at low frequencies, X sub L is approaching zero. So at low frequencies, I can replace the inductor with a short. At high frequencies, X sub L is very large. So at high frequencies, I can replace the inductor with an open. So looking at the filter circuit of Figure 5, again at low frequencies, I can replace this inductor with a short, and this makes V out equal to V source, and the output voltage will be at its maximum. However, at high frequencies, I can replace the inductor with an open, and there is no path for current through the load resistor, so the output voltage will be at its minimum. And looking at the circuit of Figure 6, Again, at low frequencies, I replace the inductor with a short, which shorts the output to ground. The output voltage will be minimum. And at high frequencies, I replace the inductor with an open, and the only path for current is through RF and R load. The output will be at its maximum. So let's look at the calculations of the cutoff frequency of an RC low-pass filter. Now, looking at the circuit in figure 7, note that I have omitted the load resistor, and I do this simply to make the math simpler. So for the filter circuit of figure 7, note that the output voltage is across the capacitor. So Vout equals Vc. And looking at the vector diagram for voltage in a series RC circuit shown in figure 8, note that when the phase angle of the circuit is negative 45 degrees, the output, which again is the capacitor voltage, will be 70.7% of the input voltage. And recalling from our discussions of series RC circuits, when the phase angle is negative 45 degrees, the resistance equals the capacitive reactance. So by setting R equal to X sub C, I can calculate the cutoff frequency by setting R equal to 1 over 2 pi times F sub C times C. And I rearrange the equation to solve for F sub C, and I get that the cutoff frequency equals 1 over 2 pi RC. So the cutoff frequency for the circuit of figure 7 is calculated at F sub C equals 1 over 2 pi RC, which equals 1.95 kilohertz. So we look at the calculation of the cutoff frequency for an RC high-pass filter as shown in figure 9. And again, I omit the load resistor simply to make the analysis easier. And with the filter circuit of figure 9, note that the output voltage is across the resistor. And again, the cutoff frequency is the point where the output voltage drops to 70.7% of the input, and this occurs when the phase angle is negative 45 degrees, as shown in the vector diagram of figure 10. And of course, when the phase angle is negative 45 degrees, resistance equals capacitive reactance. So I can calculate the cutoff frequency by setting R equal to X sub C, rearranging the equation to give us that the cutoff frequency, F sub C, equals 1 over 2 pi RC. So for the filter circuit of figure 9, the cutoff frequency is 1.95 kilohertz. Now, figure 11 shows us a simple RL low-pass filter. Again, I've omitted the load resistor to make the analysis simpler. And looking at the filter circuit of figure 11, note that the output voltage is the voltage across the resistor. And the cutoff frequency is the point where the output voltage equals 70.7% of the input, and this occurs when the phase angle of the circuit is 45 degrees, as shown in the vector diagram of figure 12. And of course, when the phase angle is 45 degrees, resistance equals inductive reactance. So I can calculate the cutoff frequency by setting R equal to 2 pi F sub C times L. And I rearrange this equation to solve for F sub C, and get that the cutoff frequency equals R divided by 2 pi L. So the cutoff frequency for the filter circuit of figure 11 is 1.91 kHz. And with an RL high-pass filter, as shown in figure 13, note that the output is the voltage across the inductor. That slide is wrong. That should say that Vout equals VL. And again, the cutoff frequency is the point where the output voltage is 70.7% of the input. And this is illustrated in the vector diagram of figure 14. And when the phase angle is 45 degrees, R equals X sub L, so I can calculate the cutoff frequency as shown, where the cutoff frequency equals R divided by 2 pi L. So the cutoff frequency for the filter circuit of figure 13 is 1.91 kilohertz. Now, in these previous examples, we've looked at the analysis of filter circuits with no load connected. But we don't filter a signal just for the sake of filtering it. This filtered signal has to be delivered to some sort of load. And this load could be another amplifier, could be a speaker, it could be an analog to digital converter, it could be a transmission line, the list goes on and on. So figure 15 shows us an RC low-pass filter with a load, with a 1 kilo ohm load connected to it. Now when I connect the load or a load to this filter circuit, it does two things. One is it changes my maximum output voltage because there will be some voltage dropped across the filter resistor RF. And of course the cutoff frequency will change also because the resistance as seen by the capacitor will change. So the first thing we'll look at is the change in the maximum output voltage. And again, when we calculate this, what we're going to do is replace this capacitor with an open, which is what occurs at frequencies approaching 0 hertz. And with the capacitor open, we're left with a simple series circuit consisting of RF and R load. So the output voltage at low frequencies, the maximum output voltage, is calculated at 8.93 volts. Now again, the cutoff frequency, as we saw with the previous slides, is calculated at 1 over 2 pi RC. But now with the load resistor connected, the capacitor sees the Thevenin resistance of RF in parallel with R load. This changes the effective resistance to 107 ohms from the 120 ohms of the filter resistor. So the cutoff frequency for this loaded low-pass filter changes to 2.19 kilohertz. Now, we talked in a previous presentation about the roll-off of these filters, and the roll-off of a low-pass filter is shown in the Bode plot of figure 16. And our roll-off is stated to be negative 6 dB per octave. And again, an octave is a change in frequency of a factor of 2. And the roll-off is stated to be negative 20 dB per decade, and a decade is a change in frequency of a factor of 10. So as shown in figure 16, We know, of course, that at the cutoff frequency, the filter has already dropped to -3 dB. But from the cutoff frequency to 1 octave above the cutoff frequency, FC times 2, the output voltage has dropped by 6 decibels to a level of -9 dB. And of course, from the cutoff frequency 2 octaves above, FC times 4, the output will drop by again another 6 decibels from 1 octave above to 2 octave above to a level of -19 dB. And of course, a decade above the cutoff frequency, the output will drop 20 decibels or to a level of -23 dB. Now, using these stated roll-off values, we can calculate the output voltage of a filter circuit. So looking at the circuit in figure 17, we have a low-pass filter with a cutoff frequency of 1.95 kilohertz. Again, at the -3 dB point, at the cutoff frequency, the output will have dropped to 7.08 volts. This is calculated by taking Vout max, 10 volts, times 10 raised to the -3 divided by 20 power. 1 octave above the cutoff frequency, we can calculate Vout one of two ways. I can either go from the maximum output voltage and apply a signal loss of -9 dB, which gives us an output voltage of 3.55 volts, or I can go from the output voltage at the cutoff frequency and reduce the signal by -6 dB. Whichever equation or formula we use, we will obtain an output voltage of 3.55 volts. And of course, 2 octaves above the cutoff frequency, I can either take the maximum output voltage of 10 volts and reduce the signal by -15 dB to obtain an output voltage of 1.78 volts, or I can take the output at 1 octave above the cutoff frequency, the 3.55 volts I had here, and reduce that signal by -6 dB. Either way, we end up with an output voltage of 1.78 volts. And to calculate the output voltage 1 decade above the cutoff frequency, again, I can use two methods. I can either take the maximum output voltage and reduce that by -23 dB, or I can take the output voltage at the cutoff frequency and reduce it by 20 dB. Either way, I end up with the same value of 708 millivolts. Now, if you look at the Bode plot that we looked at earlier, you'll note that even though the frequency response appears to be linear beyond the cutoff frequency, it's actually still slightly curved close to the cutoff frequency. So these roll-off values of -6 dB per octave and -20 dB per decibel, or per decade, are not valid when we're operating close to the cutoff frequency. So in order to obtain a precise value of the output voltage for the filter circuit of figure 17, again, using our stated roll-offs of -6 dB per octave, we obtained an output voltage of 3.55 volts at at 1 octave above the cutoff frequency, 3.9 kilohertz. But in order to obtain a precise value, we have to analyze the series RC circuit similar to our analysis method in previous sections looking at series RC circuits. So I have to calculate the value of X sub C at the frequency, which is again 1 octave above the cutoff frequency, and I obtain a value for X sub C of 60 ohms. And then I'd simply solve for V out, which equals the voltage across the capacitor, which I can calculate using the voltage divider formula, Vn times X sub C over the square root of R squared plus X sub C squared, which yields a value of 4.47 ohms. And again, using the stated roll-off of 6 dB per octave, note that I obtained a value of 3.55 volts, and analyzing the circuit as a series RC circuit, I obtained an output voltage of 4.47 volts. So using the stated roll-off values allows us to get a fairly good approximation of the output voltage. But for precise values of the output voltage, I have to analyze the circuit. So in this presentation, we looked at plots of X sub C and X sub L as a function of frequency, and we used those plots to be able to look at RC and RL filter circuits to determine whether they would function as low pass or high pass filters. Then we looked at the calculations needed to calculate or determine the cutoff frequency of low pass and high pass RC filters, and calculate the cutoff frequency for low pass and high pass RL filters. Then we looked at the roll off of a low pass RC filter and looked at the signal level at octaves above and decades above the cutoff frequency. And finally, as we see here, we looked at the analysis of the circuit to obtain a precise value for the output voltage, which again requires us to analyze the RC circuit as we did in previous sections looking at RC circuit analysis.